All right, welcome to the coding session on one-dimensional Covnets. And we're going to try the algorithm on the IMDb dataset. So we used an LSTM. The LSTM gave quite good results with an accuracy that reached the high 80s. So let's see what our 1D Covnet can do. So I'm going to make a copy of that file as I usually do. And then we're going to open it. Here there is no drive to mount, so we will be faster from the get-go. So here it is. I will say that this is a one-dimensional Covnet. Take the LSTM out here. And let's run the first few lines of code, which are pretty much loading the data. Here, this one I will delete. We don't need these intermediate steps here, but we do need to compare or to pre-process and pad the sequences at least 250 words, because that is what we've defined as the maximum length of the review. So we can run this, not an issue. This one we can delete as well. This one we delete. And here we are now at the definition of our model. All right, so now we're gonna paste the necessary code for 1D Covnets. And here we have, of course, an embedding layer. We need to embed our text and make word vectors out of it. The length of the embedding layer is 128, and the input length is max length, and in our case it's 150 words per review. If there's more, it will be zero padded. If it's less, it will be cut off. And here we have our first one-dimensional convolutional layer. 32 here is the size of the feature space, or the number of filters. And we're going to use 32 filters. The size of the filter is 7 by 7, and the activation will be ReLU. Why can we use such a big filters here compared to the two-dimensional case? Well, in the two-dimensional case we had 27 parameters, because we had 3 by 3 by 3 for our filter. So here you only have 7 parameters, which is still a lot less than 27. We have, of course, a max pooling layer, and the window here we use is 5. This is also significantly larger than we have for 2D convolution. And another one-dimensional Covnet layer. Now here at the end you see a global max pooling 1D, and there is no argument here. So basically what it does, it takes the maximum, the biggest vector of a sentence, for example. Whereas here max pooling would take the largest in a pool of 5. All right, so the rest pretty straightforward, no change. So let's get this running. Oh, name sequential is not defined. So here we're gonna have to do, to correct this, is from Keras models import sequential. All right, sequential. So now this should work. Let's run it. And let's run the code again. Oh, embedding is not defined. All right, so let's define that as well. From Keras Keras.layers import embeddings. We also need dense. Alright, so let's run this, see if it now works. No. No module named Keras. Yeah, it's Keras, of course. Here we go, run again. Cannot import name embeddings. Yeah, obviously it's embedding and not embedding. So correct and run again. So now we're good to go. And let's now run the layers is not defined. I would say from Keras import layers. All right, see if it works now. Let's go. Here we go. Finally. So it's gonna take a little bit of time. All right, so we see the result here is quite bad. We overfit from the beginning, and the validation accuracy drops very strongly. Yeah, even the training accuracy is dropping. So this is a little bit counterintuitive, because one of the main differences between a one-dimensional Covnet and an LSTM is that a Covnet doesn't really matter the order of the sequence, whereas in LSTM it does. For a 1D Covnet, what matters is only the order in the window, but whatever is outside the window doesn't really matter in terms of order. All right, so I would have expected here quite a similar result as the LSTM, but I can't figure out why it isn't.